Thanks for having us, Daniel. So today I'm going to talk about RTPEngine and doing some media processing for fun and profit. Just a quick question, who of you is using RTPEngine? So quite a lot, actually. And I hope you are going to learn a couple of new things today. Because over the last couple of weeks, we were working hard to bring new features in there you might not know about yet. They are mainly in the Kamailio trunk version and in the RTPEngine trunk version. So looking forward to getting an official release out of that. But you will hear a couple of things today, and I will do a nice demo tomorrow also on some advanced RTPEngine stuff. So what's media processing to you guys, right? I mean, it could be lots of things for different people. If you're talking about media processing, then the most trivial one is actually media relaying, right? So if you want to bypass NUTs, or if you want to anchor media at certain geographic points, you're using plain relaying. If you're using WebRTC, for instance, then encryption and decryption for bridging WebRTC endpoints to, let's say, legacy SIP endpoints are going to be a topic. Transcoding, always a big topic. Call recording, call injection, call capturing, call transcribing even, call monitoring for QS purposes are all part of this media processing topic. And we are going to focus on a couple of things today. Not all of them I mentioned are possible to do with RTPEngine, but a lot of them are, and more are going to be put in there. So today we are going to do a quick intro. Most of you already know RTPEngine, as we have seen. And we are going to focus on basic relaying, how it works, the concepts are capturing, of course, encrypting, decrypting, of course, how recording works, and also how quality monitoring is going to work with RTPEngine, and how you could leverage that for your systems and deployments. So RTPEngine essentially started off as a plain media relay, right? So internally, we used to use media proxy for major projects in the beginning. We used RTP proxy, but none of them really fit our needs. So we started to write our own. And it's used by, but not limited to, Kamailio. So there is a Kamailio module driving the RTPEngine. But essentially, you can use it from whatever application you want. There are some crazy guys doing JavaScript libraries driving RTPEngine directly. So for instance, you could have a JavaScript-based, Node.js-based WebRTC application, which is natively doing media processing with RTPEngine without going to go via SIP and Kamailio. You could also use it in Asterisk if you want, right? So it's a fairly simple protocol based on P encode, where you pass in STP bodies and you get out STP bodies. And that's essentially what the protocol does, right? Along with some media or meta information. And then RTPEngine does the rest. So the rest means it does media relaying, it does encryption, decryption, bridging between IPv4, IPv6, all these kind of things. It's kernel-based, so it's fast. So it's not unusual to have like 20K concurrent cores on a single node, for instance. It's highly available, so it's wired up against a Redis instance, and it can do seamless failover of cores. So if you have a Redis database and you have RTPEngine on an active standby setup, then if your active node dies and you have like Heartbeat or Pacemaker, CoreSync, whatever, you can move your cores over to a standby node, and with some interruption of a couple of, I don't know, 50 milliseconds or however long your IP transition takes, you're going to have your cores back up again. It's doing lots of crypto stuff, mainly for WebRTC, but not only, because obviously encryption on a media level gets more important for normal telephony cores as well, and you should really use it. It's hosted at GitHub, so it's an open source project. We get lots of contributions. Thanks a lot for 1&1 and the guys who are doing lots of amazing stuff there. And it can do much more, and we are going to figure out what that could be. So essentially, as I said, RTPEngine started off as a media relay, right? So there's this RTPEngine Kamailio module you can use in your Kamailio scripting engine, which is controlling the RTPEngine daemon. It's a user space daemon, which tries to figure out how to map certain STP bodies to other SDP bodies, trying to map ports, trying to map IP addresses, trying to bridge networks. And this RTPEngine is trying to collect data on the user space, and once it's satisfied with what it got and is certain that your call is stable, it pushes rules into the RTPEngine kernel module and then continues in the kernel from there, which drives your performance a lot, right? You have very low latency, very low delay end-to-end, and you can do a lot of concurrent calls on a single machine. And it's also doing the crypto stuff in the kernel directly, so there's no need to do any user space processing. So how it works is that you have your control plane, if you want, using SIP. And from within Kamailio and the RTPEngine module of Kamailio, you steer your RTPEngine daemon. What that means is that you pass in SDP information from a calling party, for instance, plus some meta information for RTPEngine to keep track of dialogues. So you put in like from and to tags via branches, call IDs and stuff. And then RTPEngine tries to figure out how to kind of like transform this SDP information and passes it back to Kamailio for being used to send over to the call party. And then by that, actually you wire up like 2 different call legs and having RTPEngine in the middle, as I said, to anchor media or to process media even. So that's very simple. The only thing you need to do is you need to load in Kamailio the RTPEngine module. You define some sockets. In the easiest case, you just have like RTPEngine on the same host as Kamailio. And the only thing you do, if you decide to use RTPEngine, you just call RTPEngine manage, and that's it, right? The rest is done internally in the module, but it doesn't stop there, because actually what you can do here is you can define cluster sets, and then you can figure out, okay, you have a calling party from location A, and called party being in the same location A, so you try to figure out a cluster set being like an RTPEngine instance being as close as possible to location A. And if you have calls within location B, you can steer your media path and anchor your media path as close as possible to the calling and called party. And from a daemon perspective, there's nothing much you need to do. You just start it. You can define interfaces. You can name them. So actually what you need is you need a relay IP address, 1234 in this case. And you can name them, like in that case, as X, external, right? But you can define more of those interfaces and can say, I want to have X1, X2, X3, int1, int2, int3. And you can start bridging between those interfaces. So within Kamailio, you can decide which interface actually to use for which call leg. And then RTPEngine is trying to figure out how to provide you IPs and ports, or essentially a finished SDP body to be used for this call. Speaking of relaying, encryption is basically a big part of media relays. So what RTPEngine is doing is you can transform SDP profiles for bridging SIP and WebRTC calls, for instance, or even for bridging like encrypted SIP calls to, or encrypted RTP essentially, to unencrypted RTP, because there are so many media gateways out there still which do not support encryption. Or for regulatory reasons, you need to have like a lag providing plain RTP for interception or whatever that might be. And it does the whole thing, as I said, in the kernel. So it's pretty fast. The overhead is very low. It's kind of like, I don't know, a couple of % of additional CPU to actually do the encryption. So if somebody says that encryption is hard and very heavy, that's just not true. Just use encryption, really. How it works is, again, that you pass in from within Kamailio your SDP information you get from a calling party. It could be a WebRTC-based SDP body, plus the meta information. And RTPEngine, based on the parameters you give it, is going to modify heavily the SDP. So what it can do is it can change the profile. It can add or remove ICE candidates from there. It can do the RTCP muxing and demuxing in order to make it possible to bridge like a plain RTP call to a DTLS SRTP call. And for instance, if you have a scenario where you say, okay, I'm having a plain RTP client calling a WebRTC client, for instance, Then in your request you get from the WebRTC, from the plain client, you initiate a session with RTPEngine, asking it to provide you with an RTP SAVPF profile, saying, okay, I want to have encryption and I want to have RTCP feedback. And in that case, for instance, I could say, okay, well, I want to force ICE, which means in that case that RTPEngine is going to remove whatever ICE candidates are there and it's going to put itself as the sole and only ICE candidate into the SDP information, meaning that the media will always be anchored on the RTPEngine. That's pretty important if you, for instance, want to make sure that calls are not going to go point to point rather than being relayed by your proxy. And in your reply, you just make sure that you transform it back to plain RTP AVP. You make sure that you remove any ICE candidates because your legacy SIP client might not support it. And you need to make sure that you demux your RTCP multiplexing. And from an RTPEngine daemon point of view, there's nothing else to do, right? So it just does it transparently for you. The other thing which gets more and more important for troubleshooting purposes mainly is capturing streams. I'm mentioning that particularly it's going to be phased out, like that particular feature is going to be phased out for the sake of a proper, more modern implementation I'm going to show you later. But what it essentially does is it duplicates your streams and writes it as PCAP onto your file system. So in plain, right? So if you have an encrypted WebRTC call, you get your plain RTP, or depends on if it's end-to-end encrypted, get your encrypted stream written as PCAP in your spool directory, and then you can inspect it with Wireshark, right? And that's typically used for, you know, people are calling you up, my call quality was so bad, and then you can just look into the RTP streams and see, okay, something was wrong. Oh, I'm having one-way audio, and you can look into how your RTP streams actually look like. The way it works is that Kamailio controls RTPEngine, as I said, and you just need to tell RTPEngine to capture your calls. And then it's going to write two files. Or actually, it's more, but essentially two kind of files. One is the PCAPs themselves, right, containing the RTP packets. And the other one is a meta information file providing you with SDP information so you can actually correlate PCAPs with like call information. Because in the meta information, you're going to have call IDs and wire branches and stuff like that. The important part there is you need to make sure that your file system obviously doesn't run full. So that's a bit dangerous, but you need to just do your housekeeping on that side. Again, the way it works is from a Kamailio point of view, there's not a whole lot to do. You just need to tell it to record the call, and that's it. And when you start the daemon, you need to tell it which kind of recording method you do, and that already indicates that there are more than one method. And that particular one is that you just tell it to use the PCAP method to write your RTP data into PCAP. You can tell it into which directory, and you can tell it which format. By default, RTPEngine is going to write just the IP header and onwards, like IP, UDP, RTP. But you can also tell it to put a kind of like a dummy Ethernet header into the frames as well. The more evolved way of doing it is actually called recording, because you could already figure that when you do the capturing, then you can do your manual post-processing, right? Trying with Wireshark to store your stuff as playable files, because essentially what you get is raw RTP. That's not always what you want to have. Specifically, if you want to have a feature like call recording exposed to your end customers, then you probably don't want to call SOCKS and Wireshark and all these kind of things, rather than having it natively on your system. And how the recording feature works is it's not actually recording, as we will see in my demo tomorrow. It's more like a general purpose solution where core data is exposed in meta files again. So each new call gets a meta file providing you with STP information, where you can grab your codec being negotiated, where you can grab your call IDs to correlate the calls. And what it essentially does is it just emits the RTP, which is running in the kernel, via the proc interface. And then you can actually start to read it from there on a separate daemon. So what that means is that you're not limited anymore into what RTPEngine itself can do, because, for instance, with the capturing, it's implemented directly in RTPEngine. Now you have a general purpose framework where you just get a meta file, and you get your proc interface, and you can read in real time your RTP data from there, and then you can do whatever you want with that, right? And one specific example is a decoupled recording daemon. So what you can do is you can grab it, you can send it off to a third-party server, and there you can do your media processing, like recording, transcoding, whatever you want to do on that. The way it works is it's a bit more complex, but essentially what you have for each call is a packet queue. So when you tell RTPEngine to record the call, then it's going to maintain internally a packet queue. By default, I think it's 10 packets. And it just queues them up, and you can read it from the proc file system. Where exactly is being stored in the meta information, so you need to watch that with iNotify, for instance. And you can just read it from the proc interface, and if you don't read it, they're just going to be discarded. The interesting part there is that it's safe, because if your recording daemon, for instance, dies, nobody's reading your stuff from the file system, then nothing runs full, there's no blocking or whatever. It's just going to be discarded, and that's it. So there is a recorder daemon running there, essentially doing nothing else than watching vast pool recordings for new files to appear. It parses the files to figure out if there are new calls there, if there are new streams in a call, if you have changed the codec, or whatever it might be. And then it opens the path in the proc file system. It reads the bytes as they appear, or the packets as they appear. And then it runs it through FFmpeg, or libav codec, essentially, and then emits a WAV file in real time as a result. Could be MP3 as well. In theory, it could be anything. But what you get is you get a playable file in real time out of your call. And then you can store it in your database. You can enrich it with meta information. Then you can expose it via an API or a web interface to your customers, saying, well, if you want to record the call, you can, I don't know, prefix your call with a vertical service code. And then after the call, you just grab your recording. It does it in 3 ways. So essentially, what you get by default is 3 different files, one for each stream separately, and then a mixed file with the whole call all together. All right, the way it works, again, pretty simple. You again need to tell RTPEngine when you invoke it from within your call that you want to record it. This time with the recording method proc. And what you can also do is you can add metadata in your call, which means, for instance, if you have an A party and a B party, you can tell it to write into your meta file the ID, like the contract ID or subscribe ID or whatever you need for the 2 parties in order to later figure out to which user the recording belongs to, right? So if you only want to have the A party of the call being able to fetch the recording, you would just write the A party ID there. But essentially, you can write whatever you want, phone numbers, whatever information you need later on in order to correlate your recordings to a specific user. Right, and again, from an invoking point of view, you just use the recording method proc. You provide a spool directory where these meta files start to appear. And in these meta files, then you will find the paths to the proc file system where you can actually read packets. And another thing which is brand new, I think it has been pushed to Kamailio master, I don't know, last week or 2 weeks ago or something, is monitoring capabilities. So, you know, if you provide a phone service to your users and they start calling you and say the quality was so bad, it's always hard to, prove it that it's not, or, you know. The thing is, what you have, or what you used to have before, is that you used probes in your network, which were quite resource intensive. They fetched or they captured all of the RTP traffic, tried to correlate that. For instance, Homer could essentially do that, or some commercial solutions, just for the sake of providing quality information of your RTP streams. And the interesting part there is that RTPEngine can do the same as well, natively. So what it can do is it can, since it already relays all the RTP and RTCP packets, it can very well look at that, right, and provide information on that and expose that. So what it does is it can calculate the MOS score of your streams or duplicate RTCP information to Homer in order to have real-time information there as well. And the other thing is that this information is then exposed to Kamailio, either on delete, or you can specifically query for it in a read-mite, for instance, and you can store it, right? So for instance, you could store it as part of your core detail record, where you say, okay, this was your core detail record from A to B, and the quality was this, right? And based on that, you can do your analytics and do your network planning or whatever you need to do on that. So from a Homer point of view, I think this has been released last year already. RTPEngine can report RTCP to Homer, and Homer can then graph in real time your MOS score. And that's fairly easy again. Really, everything is easy. So the only thing you need to provide is to RTPEngine the details where to send your packets to. So you provide the Homer IP import, you provide the protocol, some ID for correlation, and that's about it. And what's really new is the native style of monitoring. There are around, I counted it today, 40 parameters in the RTPEngine Kamailio module related to MOS reporting, or actually core quality reporting. So I just picked 3 of them. For instance, what you do is when you define or when you initialize RTPEngine, you define pseudo variables where the RTPEngine module is going to write statistics information to. So in our case, we say, okay, we are interested in the minimum MOS score of the core, in the maximum MOS score of the core, and in the average MOS score of the core. And when you then do your invocations of RTPEngine, for instance, in an invite, you just say RTPEngine manage or RTPEngine offer. There's nothing else you need to do there. When you have like session timer related messages like an update or a re-invite, you can do RTPEngine query, and then those AVPs, for instance, are going to be filled. And then you can use them. You can log them. You can report them to Influx. You can do whatever reporting you want to do there, or using the curl module of RTPEngine to fire it off to somewhere else. And the interesting part there is, as I said, there are around 40 parameters you have. So you can report based on the call lag. So there is A-based MOS values, B-based MOS values, correlated MOS values. There is information on the time where the minimum and maximum thresholds appear. You can report on a minimum, maximum, average jitter, latency, and all kind of things you're interested in inequality. And then you can just use that for real-time analytics of your call quality, which is quite interesting, actually. All right, so I hope you learned something new. Are there any questions?
You had mentioned that for the call recording, it's A and B leg, but do they have it where it's muxed together, or do you have to do that manually?
No, actually you get, as I said, you get 1 file per stream by default, and you get a mixed file as well. So essentially with a standard call with 2 streams, A to B, B to A, you get 3 files. One is A to B, the other one is B to A, and the third one is all of them in one.
One more question here.
Thanks for the talk. What about the performance throughput if you compare kernel version of RTPEngine versus non-kernel?
Well, essentially, you spare like the whole context switching between kernel and user space, right? And there are lots of packets in RTP, lots of small packets. So you spare quite some performance on that part. And as I said, I don't have any hard facts on that, but I'm aware that people are running, as I said, over 20K cores on one node.
I've got a question about the kernel-based. What is the best way to upgrade in this case? Because when your OS upgrade the kernel, it might break it.
Actually, if you are using Debian, which we are doing, then the DKMS framework is going to take care of that. So if you're going to upgrade your kernel, then the kernel module is compiled on the fly again against your new kernel, and it's going to be, the kernel module is going to be reinstantiated.
Thank you.
Okay, thank you. How about recording video? You didn't mention video anywhere, so...
Well, from a relaying point of view, it just doesn't care, right? Because it just relays whatever it gets. From a recording point of view, that's one of the next things to do. So from a recording point of view, what we do is we record and transcode in terms of during the recording process whatever AV codec is capable of doing. So you can do Opus, G722, G711, whatever is there. Video is not possible to record as of today, but that's certainly one of the next things we're going to tackle.
How about transcoding video? Is it available right now, right?
No.
No?
We don't do any transcoding in RTPEngine yet.
Okay.
Ole, you want? Okay, you give next.
Okay, I'll be next.
So 2 more questions, Ole, and then because they are going to be around, and again, Sipwise is a big.
Yeah, you can grab me then later on. No problem.
I'm going to do a James Bodie and dare you to find a question in this. I really want to say a few things on behalf of the Kamailio community, and that is thank you, Andreas, and thank you, Sipwise, for all the work you do for the project and for RTPEngine. Personally, I'm amazed about all these new features, and I feel way old, as Daniel told me earlier. I really need to update myself on your work, and I apologize for forgetting that we're actually using RTPEngine in the radio, so you should have been on my slides as well. Thank you.
Thanks for your kind words. Thanks.
Still one question. Okay, that's all.
Yeah, one question. Is there any sense for now to running multi-instances of RTPEngine on multiprocessor system?
No, it's multi-threaded, so there's no point of running more than one.
Okay, Andreas, really big thanks again.
Thank you.
And another round of applause.